All right, in section 4.7, we're going to talk about compounding interest. So we talked about how this is going to be a review from Algebra 2. So you should have seen most of this already. Your learning targets that you have, which should already be printed out on your packet, should have a copy of that. If you were not here and you didn't get a packet, please print that off of Blackboard before continuing to watch the video. So we need to be able to use these compound interest formulas, and the way that we're going to use them, we're going to determine the future value of a lump sum, or we should be able to determine the present value of a lump sum of money, or to determine the time required to double or triple a lump sum of money. So we're going to start with the simple interest formula. This is just a formula that helps you figure out how much interest you may earn in a year depending on, or multiple years, depending on your interest rate. So I is the amount of interest that you will get after that year. P is the principal amount invested, or in other words, the original amount, however much you put into your account at the very beginning. R is going to be the interest rate, and T is the number of years. So for example, if I put in $100 into a bank account, at the end of the year, if I still just have $100, they will pay me however much interest depending on my interest rate. So you add, let's say our interest rate was 0.05%. So I would add $5 to my account at the end of the year to then have 105. The simple interest formula is a way to determine how much interest you are going to get in that year depending on how much money you start with. Okay? All right. So whenever we compound interest, so when we start adding interest on top of it, this means that we are going to, if I put $100 into a bank account, my interest is calculated based on that $100. Let's say the interest I get then is $5. So I add $5 to that, and now my new amount that I have in my bank account is $105. So my interest is now going to be calculated using 105 instead of 100. Okay? In the simple interest, when it's not compounded, let's say I start with $105 now that I have $105, I still am going to add 5 every single time. So now I have 110. So my simple interest, my interest that I earn is only based on that original $100 every single time. So I'll get added $5 every single time until I keep adding more money. But when you compound it, that means no longer am I going to use the $100 to figure out interest, but now I'm going to use my $105 to figure out interest. So now I have 0.05% of 105. So that might be 105 point something. Okay, so this is just an example. Now, when I figure out my next interest, I'm no longer going to use my 105, but 105 point whatever. Okay, so the interest is recalculated based on the new amount of money that you have in your account. So it's being compounded. So you get more money that way. So the formula that helps you figure out how much money you get when it is being compounded together is A equals P times the quantity 1 plus R over N raised to the N times T. So A is the amount after a certain amount of years, so that's your ending amount, how much you're going to have in the account after a certain amount of time. P, again, is your principal invested, the original amount. R is, again, going to be your interest rate. And N is the number of times it is compounded per year. So maybe you put in $100 into your bank account and they calculate the interest at the end of the year to get $105. Then at the end of the second year, they use that $105 to calculate new interest and add that to your account. Then at the end of the third year, so that would be compounded once a year. Sometimes they compound it more than that. So let's say they compound it every month. So at the end of the first month, you're going to calculate your interest to be $105. Calculate your new interest. At the end of the month, the end of the second month, and you keep compounding, and you add on monthly so that you get more money every single month. The T then is however many years that you do this. Okay. All right, so let's do an example. Charlie has $600 that he wants to invest. He chooses a bank that offers him 5.2% interest that compounds monthly. So once every month. Every month we're calculating your interest based on that new amount of money that you have. So how much will Charlie have in his account after 3 years? So we're going to use our formula. Please make sure before you plug in any numbers that you write down the formula. This is going to be important for you to, the more you write the formula down, the more it's going to get into the brain and the easier it's going to be for you to remember it. So every time you have a problem, just write down the formula straight out with all the variables in it, no numbers in it. Okay? So we're trying to figure out the amount of money he's going to be left with after 3 years. So we're trying to solve for A. So we were given a principal amount. He has $600 that he's investing. That is his original amount. And we have 1 plus the rate is 5.2%. So we're going to put that in. It's 0.052. Okay, so make sure you don't put it in as a percentage. The number of years that it is, N is the number of years that it's compounded. So since it's compounded monthly, it's going to be, or I'm sorry, the number of times it's compounded in a year is 12. N is 12, and we want to figure out how much he has after 3 years. Okay. So we're going to go ahead and plug that into the calculator. Please make sure these problems are extremely important that you follow your order of operations. So do what's inside the parentheses first. So 0.052 divided by 12 is 0.0043. And 1 plus 0.0043, 1.0043. Raised to 12 times 3 is 36. Order of operations again, we need to make sure we do our exponents before our multiplication. So do 1.0043 raised to the 36th power and then multiply it by 600. So what I would do is take your 1.0043, raise that to the 36th power, and then keep that exact number and multiply by 600. So the more often you can keep exact numbers in your calculator, the more accurate your answer will be. So even when you did 0.052 divided by 12, keep that exact number, add 1 to it. Keep that exact number in your calculator, hit caret 36. Now keep that exact number in your calculator and just hit times 600. And you should get about $701.06. So with a 5.2% interest rate and compounding it monthly, Charlie makes about $101 just by having his money sit in that account. All right, how long will Charlie have to wait for his investment to double? Okay. So we know he starts with $600, and to double it, he would need $1,200. But sometimes we're going to be working with really big numbers. So if you want your investment to double, you can just say, I want 2 times my original principal amount. Okay. So this is going to work out where we don't have to work with all the big numbers. forgot. First, we need to write down our equation. So we're using there we go. And so the amount that we want to end with is 2 times the principal amount, double the amount that we started with. Rate is still 0.052, still compounding it monthly. But now we want to figure out T. We want to figure out how many years we're looking for it to double. Okay. So solving, order of operations. Okay. I have these P's here, but remember, I can divide by P on both sides so that those cancel out. And we know from before that when we take 0.052 divided by 12 and add 1 to it, we get 1.0043. So how do we solve an equation that looks like this? We're looking for the exponent. So you've got it. We are going to put it into log form. So log of 1.0043, or log base 1.0043 of 2 equals 12 times t. Okay. So if your calculator can do logs with different bases, you can just plug in log base 1.0043 of 2 and see what you get. I need to do the change of base formula. Figure out whatever that is and then divide by 12. So you should get T is about 13.46 years. So a little bit under 13.5 years. That's how long it will take him to get $1,200 to double his investment. All right, so compound interest practice. This one, same thing as what we just did. So please go ahead and fill this one out on your own and bring it to, this needs to be completed before you come to class. So with this example, A, B, and C, so both of those PowerPoint slides, go ahead and do those on your own, and then you can compare answers with your group when you come to class. If you need to pause the video and work on that, that is fine. Just replay the video when you're ready to move on. All right, so we're going to look at a new formula, the continuous compounding formula. So what this means is your interest is going to be compounded continuously. Before, we compounded it maybe daily, maybe monthly, maybe weekly, maybe once a year. So there was a set time in the year that you would calculate your new interest. For continuous compounding, you're just continuously compounding it all throughout the year. There is no set number of times you're going to recalculate your interest. It's just continuous all the time. There's an infinite number of times that the interest is recalculated, continuous, continuous, continuous throughout the year. So this is our PERT formula. So the amount is equal to P times E raised to the RT. Now, the reason why we use E in this situation, there's this whole long mathematical proof, but just to break it down, as you increase the number of times that you're compounding your interest in a year, so if you go from monthly to weekly to daily to hourly to by minute, as you increase the number of times over and over and over and over, then your ceiling, the highest you can get is that E value. Okay, so our ceiling is at for that value right there is 2.4 whatever, or 2.7, whatever E is. Okay, so that's the mathematical reason why we use E for that. It's just, and all you really need to know is that this means that we're compounding it continuously over and over and over and over and over and over throughout the year. So A is the same. That's the amount that you want to end up with after a certain number of years. Our P, principal invested, the amount that you put in. Interest rate is R, and T is the number of years. So all of these variables still mean the same thing. All right, so let's do an example. Justin has an initial investment of $2,500. His interest rate is 3.85, and it's going to be compounded continuously. So there's no set number of times in the year that his interest will be compounded. So our question is, how much will Justin have in his account after 12 years? So since we are compounding continuously, that is our clue that we're going to use the PERT equation. So anytime it says continuously, then we're using A equals P times E to the RT. Any other time when there's a set number of times that you compound your interest, then you use the other formula. Okay, so here the continuous compounding is A PERT. All right, so we want to figure out how much money he ends up with. So we're solving for A. So let's plug in what we know. Our initial investment is $2,500. So that is our P, our principal amount. E is just a number, so no variable, nothing will ever get put in for E. Our rate is 3.85%, so 0.0385 times T, which we want to know how much he has after 12 years. Okay. So again, make sure you follow order of operations. 2,500 is not being raised to that exponent, only the E is. So you need to do exponents first. E raised to 0.385 times 12. So when you put that in the calculator, E raised to, and then put parentheses, 0.0385 times 12. And you should get 1.5872. Keep the exact number in your calculator and multiply that by 2,500. And you should get 3,968 and 11 cents. Okay, so just by putting his money into account and letting it sit there for 12 years, he makes a little over $1,000. All right. Next question. How long until Justin's investment reaches $4,000? So again, we're still compounding continuously. So we're still going to use a PERT equation. Okay. And now we know that the account will get to 4,000, so that's our ending amount. But we want to know how long. So we're going to be solving for T, the time it takes. So our initial investment is still the same, $2,500, and our rate is still the same. But we need to solve for T. So let's do, last time we put this into log form. Let's use the other method this time, where we take the log of both sides. In this case, we're working with E, so it would make the most sense to take the natural log of both sides. Oops, I jumped the gun. I forgot one step. Can't forget, and this is the step that everybody always forgets. You need to divide by 2,500 first so that you just have whatever base is being raised to the exponent. So whatever base is being raised to the exponent, which in this case is E, needs to be isolated, needs to be by itself before you take the log of both sides. So we have 1.6 equals E to the 0.0385t. And now that we have that base isolated alone with its exponent, we can take the natural log of both sides. So use our power rule to bring down our exponent times the natural log of E. And we know this is why we use natural log, because the natural log of E is just going to be 1. Because base E, I have a base of E, and I need to get an answer of E. So E raised to the first power is equal to E. So I can just divide by 0.0385 divide by 0.0385, and you should get T is about 12.21 years. So a little over 12 years for Justin's investment to reach $4,000. All right, same question, same guy, putting his money in. He's got that $2,500 in the same account. The next question is, what rate should he have invested his money if he wanted his investment to triple in 20 years? So he put it in an account that has 3.85% compounded continuously, but that might not be the best rate for him if he wants his investment to triple in 20 years. So this is the same sort of thing. We're still compounding continuously. Okay, so compound continuously means we're using the APERT. Whoops, forgot some of that. The APERT equation here. So his initial amount, instead of working with these really big numbers again, his end amount we want to be 3 times the original amount. So 3 times the principal. Okay, it doesn't really matter what the principal is. We just know we want it to be 3 times that in 20 years. So what rate do we have to triple his investment in 20 years? So same sort of thing. We're still solving for an exponent. So we need to get that base isolated by itself. The base, whatever is being raised to the exponent, needs to be isolated. So we have the divide by P, and get 3 equals 20, e to the 20r. So same thing, we're working with e here. So I'm going to take the natural log of both sides. I can use the power rule to bring my exponent down to the front. And again, I know that ln of e is just 1. So ln of 3 is equal to 20 times r, because ln of e is just 1. Divide by 20. Put that in your calculator, and you should get 0.0549, which means 5.49% is the rate that Justin needs his interest to be compounded continuously so that he can get his investment to triple over 20 years. Okay. So it's a matter of just setting it up and just figuring out what it is that you're solving for. Okay. All right, so the last two slides that you have in your, so the next slide that you have, the continuous compounding practice, Chloe invests her money in a bond trust that pays 7.2 interest compounded continuously. That needs to be completed before you come to class, so go ahead and try that on your own, see if you can figure out the answers for those two, and then you can come to class and compare those with your groups. But those need to be completed before you get to class. The last two slides, the computing effective rate of interest, go ahead and just leave those for now, and we will talk about them when you come to class. After we've discussed a little bit all the stuff that we learned in the video, we'll talk about those last two slides before I give you some time to practice. All right, so make sure you have those other two examples completed, and I will see you in class.